by talking about an additional way to measure the size of an angle. So you guys certainly are familiar with degrees, right? That's one way of measuring the size of an angle. Another way is with a unit called the radian. Now, maybe if you took honors geometry, you talked about radians there. If you took regular geometry, do you remember talking about radians at any point? Okay. So this is the idea. So say we have some angle here. What we're going to do is we're going to imagine that the vertex of this angle is the center for some circle. Where the radius for that circle is just 1 unit. This portion of our circumference, this arc length, is going to equal the radian measure for the angle. So when we talk about radian measure, it's just another way of describing the size of the angle, this time based around distance, like something measurable, as opposed to like a degree, which is, again, you could use a protractor or whatever to measure it, but this is based on a distance, like a unit of length. Everybody's okay with that idea? Now, whenever you introduce two different ways of measuring something, immediately you want a way to go back and forth between them. You want a conversion factor. So like if I have inches and I have centimeters, I want a way to convert inches to centimeters, so centimeters back to inches. If you remember, I don't know, probably some science class, 1 inch is 2.54 centimeters. Maybe that's familiar, sounds familiar, maybe it's not. Maybe I should have been like inches and feet, but you know. But we always want a conversion factor to convert between two different units if they're measuring the same thing, right? So that's what I want to do next, is I want to convert or find a conversion factor for radians to degrees. So let's say we have a circle with radius 1. And let's make the angle for this circle a 180-degree angle. So I know that 180-degree angle is going to be equivalent to this radian measure. Now, how much of the circle's perimeter is that, or how much, I should say, how much of the circle's circumference is that radian measure? Half, right? Would you agree? Does anybody remember the formula to find the circumference of a circle? From geometry, it was a long time ago. 2 pi r. And the radius in this circle was 1. So what do we have here? We have that 180 degrees is equal to pi radians. And that will be our conversion factor. So whenever we need to convert between degrees to radians or radians to degrees, that's the conversion factor we're going to use. The way that I would do that conversion would be the same way that you converted units in your science class, like in your chemistry class, where you convert from grams to moles or something. We'll do like that same dimensional analysis, I think is the name of that technique. So let's buzz through a couple of examples. So let's say we want to convert 90 degrees to radians. So I'll start by building out my dimensional analysis here. So I remember when I did this in my chemistry class, if my unit here is in degrees, what unit needs to be diagonal to it? Also degrees. So that's where the 180 degrees is going to go. And then the pi radians should be on top. So the degrees will cancel, and we're left with 90 pi over 180 radians. But what do you notice about 90 pi over 180? What do you notice about that fraction? Maybe just the 90 over 180 part. It can simplify. Yeah, we can reduce that fraction. What does 90 over 180 reduce to? 1/2. So this can just reduce to pi over 2 radians. And typically, if we can leave our radian measure in terms of pi, that's what we prefer to do. If you type that into your calculator and press enter, you're going to get a non-terminating decimal. We've talked about exact answer already, right? Did we talk about exact or no? Okay. In most cases, we prefer to leave exact. So pi over 2 is the exact version. 1.57, yada, 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 is the decimal approximation. Typically, you want to have the exact answer if we can. Not wrong, depending on the directions, though, if you rounded it, depending on what the directions told you to do. But if not, instructed to round. Try to leave it exact if you can. Not every case would you be able to do that. If it was 57.2 degrees or something, probably not going to try to leave that exact. I'll just round that one because I know 180 doesn't, reduce with 57.2 nicely. You know what I mean? All right, let's do the next one. 152 degrees to radians. So I set this up the exact same way, right? Since it's just a degree to radian computation. And I'm left with 152 pi over 180. And now I can reduce that a little bit, right? 152 over 180. They're both even, so I know I can reduce them, right? So I'd go down to what? 76 over 90. And that again to 38 over 45, and I think you're stuck there. Does that sound right? Or if we rounded that, you would have gotten like about 2.653. Again, that's a funny enough fraction that if you gave a decimal, I would not be surprised if they gave a decimal. Tommy? No.
Where'd you get 45?
Joey?
Under 38 in the denominator?
Yeah, so I divided the top and bottom by 4. So 152 divided by 4 was 38, and then 180 divided by 4 is 45. So I did divide by 2 twice, right? Like 76 to 90, and then 38 to over 45. You know what I mean?
Yeah.
Again, I said it aloud, but I didn't write it down. But okay, yeah. But if you're not sure, holler. And I'm happy to go through the detail again, or if we need to write down some stuff, because it's like, yeah, you did a lot of stuff there in words. Can you show me it's like in writing? Happy to do that kind of thing too. Just let me know. Again, I'm happy to meet you guys where you are, but it's a feeling out process in the beginning of figuring out exactly where we are.
Yeah.
Which is okay. No big deal. All right. C says we're going to have 2 pi over 5 radians. Now this time, notice we're converting from radians to degrees. So if the radian is on top, what unit needs to be on the bottom? Radians. So we'll have pi radians on bottom now, and 180 degrees on top. Is this feeling okay? Does it help to kind of just think about it like a chemistry thing that we're already kind of familiar with? I try to do that as much as I can if there's something I think you've already done. So the units cancel out, and we're left with just degrees. So this would be 2 pi times 180 is like 360, and then over 5 pi. What do you notice about 360 pi over 5 pi almost immediately? Yeah, what can reduce?
365.
Okay, so the 360 over 5 can reduce and the pi's can reduce. Usually, like, I'd like to reduce the pi's here even, so I don't even have to carry them through, but, you know, tomato there on that one where you do that at. 360 divided by 5 is 72. Are you impressed that I do that quickly in my head? You wanted the trick to how I did that quickly in my head? 360 is 36 times 10. I divide 10 by 5, that's 2, and then 2 times 36 is 72. So I didn't do like the long division in my head. That's nutso. Not wasting my time doing that. Let me just break the 360 into easier chunks, find a chunk that's easy to divide by 5, and then put it back together. You know what I'm saying? Is it necessary that you're able to do that in your head? No, of course not. Like, use a calculator, write stuff down, not an expectation that you're doing that in your head, but I like to share those things. It looks kind of impressive. It's like, whoa, how'd you do that? You know, talk it through. And our last one says convert 1.6 radians to degrees. So this will be like the same setup, right? Because we're still going radians to degrees. You know, radians cancel. And then 1.6 isn't in terms of pi. I'm not going to bother trying to multiply 1.6 times 180 and then write that over pi. That's a bunch of garbo, right? That's a crazy looking number. It's a degree. We don't mind degrees being decimal, right? Like, that's perfectly normal. So this is just all going to go into a calculator. If I type this into my calculator, I should get about 91.673. If you want to type that into your calculator alongside, just to double check me, you're welcome to do so. Or if you're like, ooh, how would I even type that into my calculator? I can show you on the screen and how to like the most effective way of typing this. If you're interested, if not, that's okay. How were you feeling on this converting back and forth? Piece of cake? NBD? I would hope so, right? Like all we're doing is like multiplying some numbers together. The trickiest piece is just making sure you have that ratio, the right thing on top and bottom, but you know, if you just remember the units need to be diagonal, you're in good shape. The next thing we're going to define is an arc length formula. So we have two different versions of this formula. So if S is your arc length and R is the radius of your circle and theta is that central angle, in one formula we have theta measured in radians, in the other it's in degrees. So we just have two formulas. The trick is making sure you're choosing the correct formula. What's going to tell you which formula to choose? How the angle is measured, right? If it's measured in radians, I'd use the first formula. If it's measured in degrees, I use the second formula. That's it. So we have these two different formulas. They're both measuring arc length in a circle. So let's do a couple examples there where we do a calculation to, or practice doing these calculations and selecting the correct formula and all that jazz. Sound good? Okay. So far, everything's all right? Not too fast? If I start getting ahead of myself or moving too fast, holler at me. It's like, hey, just can you pause for a minute while I catch up? Or can you slow down and say that again? Or explain that a little more? You know, like as much as I'd love to be able to live inside your head, it sounds terrifying actually. I don't know what's going on in there. I'm assuming if you don't say anything, everything is fine. If it's not, I need you to speak up and say like, hey, you lost me there or whatever. I promise you, if you're lost, someone else in the room is lost. You're not alone. So just be a good advocate for yourself and everything will be okay. All right. Running through some examples. The part A, or example A, says solve for S if R is 1.4 meters and theta is 0.98 radians. So that's what I'm looking for there, right? That tells me which formula to use. Since that theta's in radians, I use the radian version of my arc length formula. Now I just plug in the value for R and theta and type that through in my calculator. And I would get 1.372. What unit should that have? Remember, arc length is a length. So if I look at the units of R and theta, which one would give me the arc length? R. Should be the meters, right? Yeah, so this should be meters, measured in the same unit as the radius. Is everybody okay with that? Since it's an arc length, we would want to be using a length unit for it. Okay. Let's do B. It says solve for S if R is 3.8 and theta is 40 degrees. I noticed that the theta is in degrees this time. So I'm going to use my other formula. Everybody's okay with how I selected that? And then we just plug in our values. Show you on your calculator a little nice trick when we start having these fractions like this. So if you press the alpha button, that's the green one, and then the y equals button in the top left-hand corner, that opens up the fraction menu. If you choose that option number 1, that gives you the horizontal fraction bar. So really whenever I have a calculation where I have a horizontal fraction bar, especially if there's like stuff like operations going in the numerator and denominator, I like to kind of type it that way. That just gives me the peace of mind knowing that if it looks exactly like the piece of paper, the calculator's doing exactly what I think it is. If you use the division symbol there, particularly if there's operations going in the denominator, it's very easy to screw that up with your parentheses. Josh? Yeah, it's alpha, that's the green one. Y equals, that's the upper left-hand corner. And then option 1 will give you the horizontal fraction bar. Cool? Joey, what's up? Oh, okay, no problem. Couldn't tell. So when I do that, I got, what was it, like 265 something? 3. And again, the unit here should be inches. Very good. Yeah, matches the radius unit. Let's do example C now. Now this says solve for R. Notice it's not S. But it does give me S is 18 centimeters and theta is 2.13 radians. Again, this is what I'm looking for initially. That tells me that I'm using the first formula. So if I plug things in, S is 18, R is my variable, and theta is 2.13. To solve for R, I should just divide both sides by 2.13, like some Algebra 1 algebra, right? Should be no big deal. When I type that through in my calculator, I get, I should say about, probably there, whatever, 8.451. And the unit for that radius should match the unit for the arc length S, so it should be centimeters. How do we feel on doing these kinds of problems? No big deal, right? Like, I just got to pick the right formula, put the stuff in the right places, do some Algebra 1 algebra, on to nice town, right? Who remembers what a sector looks like from geometry? Does anybody remember what a sector is? Because that's the key there, right? For this it says, find the perimeter of a sector with central angle of 1.7 radians cut from a circle with 5 centimeters. A sector is a pizza slice, basically. So like if you have your pizza and you cut it up into, you know, eight slices or whatever, one of those pizza slices is a sector. I'm talking about a round pizza, not a Jets pizza. Just to be clear, right? We're in the Metro Detroit area, so I want to make sure we're talking about round pizzas and not squares. So if I draw this picture, that's like my sector, right? So this angle right here is my central angle. Each of these straight sides are a radius. And this side, the curved side, is going to be an arc length. Since that central angle was measured in radians, I'm going to use the formula S equals R theta to calculate S. Once I've done that, my perimeter is just going to be R plus S. Is everybody okay with that? Again, perimeter is just like the distance around something. So it's this side plus that side. Does that feel okay there? Once you know what a sector looks like, not too bad, right? I just used an arc length again. Yeah, okay. No problem. All right, one more example in this section. All right. A car has 18-inch diameter tires on it. The car is traveling at 15 miles per hour. How many revolutions per second are the tires making? So this problem, although it doesn't read like it at first, is just a unit conversion problem. So we're going to start with our speed. And I want to end in revolutions per second. That's our goal. So everybody read the problem and kind of identify that that's what really needs to have happen. Okay. So what I'm going to do is we'll start with our speed, 15 miles per 1 hour. And I want to start by converting well, at least hours to seconds, right? Because I know it has to be in, that unit needs to be in seconds right away. I can see that pretty clearly. So let's do that to start with. So how many seconds are in an hour? And maybe you don't know. Well, what do you know? There's 60 minutes in an hour, right? Well, I know that. And then I know that there is 60 seconds in 1 minute, right? Maybe you knew there was 3,600 seconds in an hour. If you did, you could shortcut to there. I just wanted to kind of talk through that piece. So we've kind of done this part, right? We've taken hours to seconds. Now somehow we need to turn miles into revolutions. Here's the key. Is that diameter of the tire is going to be our key. So because the unit for the diameter of our tire is in inches, I'm going to first start by converting miles to inches. Everybody's okay with that? Now, I'm guessing that nobody knows how many inches are in a mile. What do we know a mile is? 5,280 feet? I know. Do I expect you to have these things memorized? No. And then I know 1 foot is this one I would expect. 12 inches, right? Everybody's okay with that? Okay. So if we pause here for a moment, look at what we've done. We've converted miles per hour into inches per second. Does everybody kind of see where we're at in the problem? Again, I just want to pause here and kind of, before we do this final step, because the final step's the trickiest one. Somehow now I need to convert this linear unit of inches into a revolution. What I need to know is how far does this bike travel, how far does the tire go with 1 revolution? That's going to be my final conversion factor, right? So we have a wheel, right? Let's say the bottom of the wheel is this point. As that wheel turns, how far is that distance going to be? Any ideas? I don't want a number, I want an idea. What do we think? I'm not looking for a number, I'm looking for like something else. Let's imagine this, right? We have our wheel, right? And let's put like a piece of tape on it. And as that wheel rolls, it lays that piece of tape down on the ground. Right? So like it rolled and it left like that piece of tape on the ground. How far is that piece of tape? What? Right, just 1 revolution. How long is that tape? So that wheel makes 1 complete turn. As it's making that complete turn, it's laying that tape down. What's that? It's not 12 inches. If I look at this picture, how long is the tape? It is one circumference of the wheel, right? The distance traveled by any circular object in one revolution is the circumference of that object. So that's going to be my final conversion factor. Knowing that one revolution is equal to one circumference. So our car has 19-inch diameter tires. How far is one circumference for a tire with 18-inch diameter? Remember, a circumference is 2 pi r. So what is the r if I have 18-inch diameter? 9. Because we remember that a radius is half of the diameter, or the diameter is twice the radius. Whatever way of thinking about it is okay. Now if we look, now I know I'm going to be in revolutions per second. And I'm done. I just have to multiply this out. Is everybody cool with the plan? Okay. I'm going to fire up to do this. I'll fire up my calculator. I'm going to get that horizontal fraction bar. What do I press to get that horizontal fraction bar again? Alpha y equals. And then we'll just pick the first option. In the numerator, I'm just going to type in everything that's not a 1. So I'm not going to bother with the times 1s. So I'll have 15 times 5,280 times 12. And in the bottom, again, everything that's not a 1. So I have 60 times 60 times 2 times pi times 9. And then we'll just press enter. And I get about 4.669 revolutions per second. That go okay? It's probably as hard as it gets for this section. Okay? And again, like, hopefully we walked through that carefully enough that you kind of got the hang of that. It's not so bad, right? It's just basically a big unit conversion problem. All right. In section 2, we're doing the same thing that we've already done, just doing right triangle trig. The only difference from what we did on day 1 to section 2.2 is that I could also give you angles and radians. Does that really affect what you're doing? No. What's the only thing I have to be careful about? That I'm changing the mode of my calculator appropriately before I try to do sine, cosine, or tangent. Right? The mode on my calculator needs to match the angle in the problem. Everybody's okay with that? Josh? Absolutely. And then I have one other addition. So, you know how, like, we've defined sine as opposite over hypotenuse, and cosine as adjacent over hypotenuse, and tangent as opposite over adjacent. Why don't I have, like, instead of opposite over hypotenuse, why don't I have something for hypotenuse over opposite? Why don't I have a trig function for that? Like, why isn't that a thing? Guess what? It is a thing. We're going to define it right now. So, given right triangle with acute angle theta, we know sine, cosine, and tangent are opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent respectively. We have three new trig functions. We have cosecant, which we abbreviate as CSC. We have secant, which we abbreviate as SEC. And we have cotangent, which we abbreviate as COT. If I look at the definition of sine and cosecant, what do you notice about their definitions? They're reciprocals of one another. Excellent. What do you notice about the definitions for cosine and secant? They're reciprocals. And what about tangent and cotangent? Also reciprocals. So, if it's me, the way I memorized the definitions for these three new trig functions is not their definition. I just memorized that cosecant is the reciprocal of sine. I already know the definition of sine, so it's reciprocal. That's easy to remember. Secant, reciprocal of cosine. Easy enough. I know the definition of cosine. I can write its reciprocal real easy. Cotangent, the reciprocal of tangent. Easy enough. If I know tangent, I know it's reciprocal. That's really easy. So hopefully it's really easy to remember that tangent and cotangent go together. Those are reciprocals, right? The trick is how to remember that cosecant goes with sine and not cosine, for example. The way I remember that is that no cos go together. Like cosine doesn't go with cosecant. The cos don't go together. And if I remember that, I'm usually in good shape. Does that feel okay? Again, however you choose to remember it is fine. I'm just talking through like the little tricks that I remember coming up with as a high school student when I did the same thing. All right. Let's run through some examples of just kind of doing this. You'll see some things that have sine, cosine, tangent, cosecant, secant, cotangent, so we'll practice a little bit with that. In addition, we might see stuff that has radians instead of degrees, so we'll practice a little bit with that, but this is not any new idea here that we didn't already practice a bit. So it says find the exact values for all 6 trig ratios for theta in the right triangle. Okay? Well, maybe I'll just start by writing down my definitions. So again, cosecant goes with sine, so those are reciprocals. Secant goes with cosine, so those are reciprocals. And then cotangent goes with tangent, those are reciprocals. So just kind of start there, write down my definitions. Now I just have to kind of look at my picture and plug these things in, right? Okay, so if I look at sine theta, sine is opposite over hypotenuse. What's the opposite? 5. Excellent. What's the hypotenuse? I don't have it yet. It's not in the picture. How am I supposed to figure that out? I'll give you a hint. What kind of triangle is this? Right triangle. So if I have two sides of a right triangle and I want to find the third side, what do I use? The Pythagorean theorem. Yeah. So I know that a squared plus b squared is equal to c squared. Now, what do I have to remember that's about A, B, and C? One of them is special. Which letter is the special one? C. What does C have to be? The hypotenuse, right? The legs doesn't matter whether you call that A or B, but the hypotenuse must be C. Everybody's cool? Okay. So the legs are what we're given, right? 5 squared is 25. 2 squared is 4. 25 plus 4 is 29. And then to get rid of the squared on the c squared, we'll square root both sides. So that hypotenuse is the square root of 29. Everybody feel good there? Okay. Now, is that the way we'd leave that final answer? No, what's wrong with it? Square root in the denominator. How do we get rid of that again? Wonderful. Yeah, let's do that real quick. So remember, when I multiply a number without a square root by a number with a square root, nothing happens. We just stick them right next to each other. And square root 29 times square root 29 is regular 29. So there's an answer. Now, let's do cosecant. Look at your work for sine theta. Remember that sine and cosecant are just reciprocals, right? So shouldn't I just take my answer for sine and flip it and then be done? Yeah, but let's be careful here. Because if I take the answer for sine that I have circled and I flip it, what's going to be wrong with it? Square root in the 29 is going to be back in the denominator. Oh my God. Let's just take this one then. Right? Like that's still the answer. We didn't really change that other than what it looks like. Let's just do that. Woo! That was easy. I like that, Mr. Kulik. Let's do that again. All right. Cosine should be what over what? 2 over square root 29. Any questions on where Brooke got that from? I think it was Brooke that answered. I wasn't looking when you said it. Still figuring voices out, but it sounded like that was the direction it came from. Good. who can rationalize the denominator for 2 over square root 29 without writing it down? Who can just say the answer by looking at it? Can anybody do it? Go ahead, Edie.
2 square root 29 over 29.
Yeah. That's correct. If you need to write that down, you're welcome to keep writing it down. I'd like to get to the point where, like, we can just write the answer without showing the work for it. But if you still need to, like, that's always going to be fine. But, you know, I'm of the mind, like in the notes, we'll do it once, and then we'll shortcut so we just don't have to speed things along. We don't have to take forever doing this. All right. Who can tell me the answer for secant? Someone other than Edie. You're doing a great job. I just want to spread out the yeah, Nicole.
Square root 29.
Awesome. Yes. So again, hopefully what Nicole did is she looked at that one and it's like, I'm going to take the non-rationalized answer and flip it, because if I take the rationalized one, I'm back in the same boat as before, and I got to do a bunch, they rationalize again, and then have to reduce, and it's like a whole thing. Let's not.
Yeah.
Let's not. All right. Who can do tangent? Yes, sir. 5 over 2. And on that same note, then, what's cotangent? 2 over 5. Just the reciprocal. Nothing fancy happening there. So the things I highlighted is what I used to get the other answer, but the things we circled were the finals, right? What do you guys think? Pretty okay? All right. What if we ask the question this way? Let theta be an acute angle of a right triangle. If sine theta equals 1/3, find the values of the other 5 trig ratios for angle theta. Who says, Mr. Kulik, this sounds really different than the previous problem? Guess what? It's the same as the previous problem. It just didn't give you the picture. So it's really the same problem as the previous. We just didn't get a picture to go with it. So let's start by drawing our picture. Yeah? So I'm going to draw it so it's like oriented the same way as before, just so I can really hammer home to you guys that this is the same picture, right? So relative to our angle theta, we said that this side was opposite, this was adjacent, this is hypotenuse, right? And we're told that sine theta is 1/3. And I know sine is opposite over hypotenuse, right? So I know that side is 1 and that side is 3. It is now the same problem as before. Everybody see that? Let's find the adjacent side and then we're going to quit, because I'm going to hope that you could do the same thing that we did before and just fill in the numbers, right? Does everybody feel confident they could do it from here? You like how that this is really just the same problem, we just asked it in a different way? It's like, I just had to draw my own picture here. All right, Pythagorean theorem this up. So I have a squared plus b squared equals c squared. What are we going to put in for a?
What
1. What goes in for B? Nothing. That's our variable, right? Okay, good. And C squared then is 3. Okay. So 1 squared is just 1. I'll subtract that from both sides to get the B squared by itself. 3 squared is 9. 9 minus 1 is 8. And then we square root both sides. Is everybody okay with me kind of scooting through the algebra a little bit quick there? But I think it was fairly straightforward algebra. Then I talked through what I did, right? Can we simplify the radical square root 8 at all?
Yeah.
Yes. Good. So the easiest way to simplify a radical is saying, okay, can I break this up into a factor that is a perfect square? So the square root of 8, I can think of the square root of 4 times the square root of 2. And I like that because the square root of 4 is a perfect square. That's just 2 root 2. And we're good, right? Is everybody happy? All right. I'm going to do one pair of ratios just because I want to do the rationalizing here for a second because I think it'll be worth showing. Cosine is what over what? Cosine? Adjacent over hypotenuse.
Oh, yeah.
Great. And what's the adjacent? What's the hypotenuse in this problem?
2 square root 2 over 3.
Great. And that's fine the way it is, correct?
Mm-hmm.
What's secant going to be then? 3 over 2 square root 2. Now, if I want to rationalize the denominator for secant theta, what do I multiply to the top and bottom?
Square root 2.
Just square root 2 is enough. If I do 2 square root 2 to the top and bottom, is that okay still? It'll still be fine. What are you going to have to do, though? You'll have some reducing to do at the end. You'll be guaranteed to have reducing at the end. It's not the end of the world, but hey, my life is difficult enough. I like to just make good choices and avoid work in the future. So I'm going to have 3 root 2 at the top. And then I'm going to have 2 times 2 at the bottom. Right? The first 2 is just from that, from the 2 on the 2 root 2. And the second 2 is from the root 2 times root 2. Everybody can see that. And then I know that 2 times 2 is just 4. And I'm not going to do the other 4 ratios because it's not really much different. And we already practiced doing trig ratios once already, right? What if I asked you to do, where did my, oh, there you are. What if I asked you to find the exact value of pi over 6? Oh no! So you hear the word here, exact value. What do you know we're going to have to use? I know I'm going to need the 30, 60, 90 or 45, 45, 90 triangles to do this, right? Okay. It's pi over 6. What do I do with that? Just convert it to degrees, man. Right? That's a radian measure for an angle. That's fine. I know how to convert that to degrees. So that's just sine of 30 degrees. Oh, okay. So all I need is that 30, 60, 90 triangle then, right, Mr. Kulik? You betcha. So sine of 30 is just 1/2. Dunzos, right? So if you run into a radian measure on one of these kinds of problems, what are we going to do? Just convert it to degrees and do it the same way, man. Like, let's not make it harder than it needs to be, right? Like, we already know how to do it with degrees. Just convert it to degrees. It's not like I'm memorizing these things twice. It's not, right, Mr. Gulick? I know it in degrees. Can I just do it as degrees? Yes. Yes. Okay. Everybody feel okay there? Again, not anything new. We just, like tacked on the subroutine of like changing it from radian to degree before we did the problem, which I think we can handle. I hope. What if I ask you to do like sine of 17? How do I do something like that? Did the directions say I have to have an exact answer? No. So decimal is going to be fine. How do I get the decimal for sine of 17? I type it into my calculator and press enter. That's it. That's all we're saying. Before I type it in, though, what should I check? The mode that my calculator's in. If we've been doing this and converting back and forth from radian to degree, it'd be a pity to get the problem wrong because I put it in the wrong mode. What mode does this one need to be in? Degrees. So let's just check real quick. Yep, I'm in radian mode. I switch back and forth in all my classes. Especially like I have AP Calculus. Everything in AP Calculus is in radians, always. So I'm always converting back and forth. So what? 292 would be my answer. 0.292. Sounds good. What if I wanted to do secant of 78? There's no secant button on my calculator, Mr. Kulik. How am I supposed to do that? Okay, true, there is no secant button on your calculator, but secant is related to which of the other three trig functions? Cosine, because they are not inverse, it's the R word. Reciprocals, right? Inverse means something different. I know what you mean, but we're going to work on vocab, make sure we're saying the right things, even you know. So if you're communicating with someone other than your math teacher knows what you're trying to say, we're making sure we say the right things. So what I'm going to do is I'm going to do cosine 78, and then I'm going to press the reciprocal button. That's that little x with the -1 exponent. It's right under the math button there on the left-hand side. That does the reciprocal for me. So my answer should be 4.810 if I rounded to 3 decimal places. Cool beans. All right. And, one last example problem and we're donezos for today. Sound good to you guys? I know I'm so tired too. This weekend felt fast. Did it feel fast to you guys?
Yeah.
Yeah, I know. It's a bummer. They're all going to start feeling faster though, especially like once the sports start really cranking up into high gear. If you're a sporter. All right. So this direction says solve the triangle. When I say solve the triangle, what do I mean? What is that direction telling us to do? Find all the side lengths and all the angle measures, right? Okay. One of these is basically free. What's basically free?
The angle.
The other angle, right? What do I know that other angle has to be? 49, right? How do I know that? The sum of the interior angles of the triangle has to be 180. Or, since it's a right triangle, the two acute angles have to add to give you just 90. So I know if I call this side, or that angle x, boom, done. All right, let's find that hypotenuse next. I'll call that, well, let's call it h for hypotenuse. That'll be a good name to call that. If I'm using that 41 degree angle, and I'm using the other side that I know, and I'm looking for side h, which trig function should I use? Cosine, very good. So I'll say cosine of 41 degrees equals adjacent over hypotenuse. I'll multiply both sides by h to get it out of the denominator, and then divide by cosine 41. And then that's calculator time. I'm going to leave that calculatoring to you. Is that okay with you guys? And I'll call that one, that other side, L for leg. If I want to solve that guy, I'm going to use, oh boy, don't do that. Use that 41 and 12 again, and this time L. Which trig function would I want to use to solve for that L if I'm using the 41 degrees and the leg 12? Tangent, very good. So we'll do tan 41 equals opposite over adjacent. Multiply both sides by 12, and then it's calculator time. And again, I'll let you guys punch all that gobbledygook through if you choose. Right? We're okay with just getting into the type into our calculator stage here. Sorry, I'll make that not so low on the screen. I see people craning their necks, looking around their tall friends, trying to see the board there. Apologies. How'd today go? It's all right? Didn't seem too bad? Pace okay? Not going too fast? Leaving nobody behind? If you're saying that, oh, Mr. Kulik, I'm already in trouble, please make sure you're finding some time to come see me and make sure we're getting on the same page. So the homework set for this is 1 through 42. I know that sounds like a lot, but like, guys, think about what we did. Like, you're converting units and like changing things from degrees to radians and like typing like sine 17 in your calculator and pressing enter. Like, there's a lot of problems there, but they're not bad. The problems, if you look in the OneNote at the problems page, this is the list of problems. If you choose to do your homework in OneNote, please don't write your answers next to the problem. Like, if you want the problem sheet on the same page as your work, that's fine, but like make a new column down the side and label it like 1, 2, 3, 4, 5, and like write your answers on any work there rather than trying to cram it in next to the problem. Please, 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 pretty please with sugar on top. If you choose to do your work in a notebook, totally fine. We'll talk next class on how to get something from your notebook into the OneNote to turn in your homework. Okay? I'm not going to worry about it today because, well, if you have your homework done, your example can be done with your homework. If your homework isn't done, well, then you'll just get to see the example or whatever. But if you wanted to follow along, you can follow along, whatever. Does that sound good to you guys? Okay. Any questions about anything else for me? Oh, I do have one more question for you. Does anybody have their syllabus sign-in sheet that hasn't turned that in yet? If you haven't, I'll still take it. And if you've forgotten again, ooh, buddy, write yourself a note because it's been a couple of days now. I was hoping for them in by today. I don't have a syllabus, but I have a sheet. You're welcome.